Hello again. Thanks for joining us on Space Nuts, the astronomy and space science show. I'm your host, Andrew Dunkley. It's great to have your company. Coming up in this particular episode, not the last one, not the next one, but this one, we're looking at reflecting sunlight onto the moon. Why? Well, because they need to. That's the only reason. And the expansion of the universe, they reckon, may have slowed down after the Big Bang. Now, we've had a lot of people writing into us, emailing, messaging us, voice messaging us about this particular phenomenon. So we're going to take a look at it. And coincidentally, we've got two questions about it today. So we'll tackle those. And a real big surprise from one of our regular sender-inners. I'm not going to reveal anything. I'm just going to let this one fall as it may, and we'll do that towards the end of the show. But I think you're in for a shock, a surprise. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Joining me to talk about all of that is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. You're looking well today.
You're looking sprightly yourself, sir.
That's good.
Yes. You've been to Canterbury.
Yes, I have. Just down actually for the day yesterday. I drove down on Tuesday night and drove back last night.
How long's the drive from your place to Canterbury?
3 hours and 40 minutes.
Oh, that's not bad.
No, it's all right. It's fine.
It's 5 hours from here.
Yeah, that's right. It's a different kettle of fish. The
Yeah, because you've got roads and everything.
We've got roads. We've got effectively dual carriageway all the way. So you're not.
Yeah, well, you've got dual carriageway. We have to use carriages.
Yes, and horses.
Yes.
Yeah, I've done that drive from Dover to Canberra many times when I used to live in Coonabarra, and that's the way I went down. And you've got two choices, haven't you? You can go one way or the other.
Yes, and they both take just as long.
Just as long.
There's no shortcut.
No, remember it well.
Yeah, no direct flights either.
No, that's right.
It's a real pain. What were we talking about? Oh, yeah. So what took you down to Canberra? Just a regular meeting thing?
Yeah, meetings. One of which was sort of harking back and harking forward. You remember I was in Vienna in February at the Committee on the Peaceful Uses of Outer Space. There's
Yes.
a scientific and technical subcommittee. And I was at the meeting there doing my thing. So there's been another meeting of the committee, which I wasn't at. This is the full committee on the peaceful uses of outer space. And so basically what I was getting was a report along with colleagues in the Department of Industry from my colleagues in the Space Agency who were presenting on what actually happened.
Okay. Did you get lunch?
I did actually.
Because you know what that would have been? A piecemeal.
Well, yes, it was actually piecemeal. I had lunch courtesy of two of my colleagues. One of them gave me a Snickers bar and the other gave me a mandarin. They must, oh, sorry.
What a wholesome lunch.
Oh, it was good stuff. But it was very kind of them. It saved me kind of taking my face away from the computer and going and getting something.
Yes.
Actually, one of them bought me a coffee later.
Oh, very good. Yes. Oh, I'm glad it was a fruitful event.
It was fruitful, yes. Quite snickerful as well.
Yes. All right, let's get on with it. We've got a couple of interesting things to talk about. These are fascinating topics. Now, we have been watching with interest the build-up to sending human beings back to the moon, the Artemis project being one of them, but I think a couple of other countries are looking at doing the same thing. One of the challenges is if you're going to put people on the moon and maybe leave them there, which is the long-term goal, setting up a moon base, you've got to be able to, attain continuity. And that means power. And that means that there are a few stumbling blocks to overcome. And this is one of them.
Indeed. And it's really comes about because of the particular part of the moon that everybody's interested in. which is the deep craters near the moon's poles, and in particular those craters near the moon's south pole, because we think there's water reserves there, literally frozen water in the bottom of these craters, because they never see sunlight. Now, if you're going to send astronauts to the moon to excavate this water, and by using electricity, dissociate the water into hydrogen and oxygen to make rocket fuel, that's one of the uses for that, then you need power, exactly as you've said.
Yep.
And so suddenly you've got this dichotomy. You're on a world that is bathed in sunlight and no atmosphere to attenuate that sunlight. It beams down very strongly. Put a solar panel there, you're getting electric shocks from it straight away. But on the other hand, the place everybody's interested in is in deep shadow, and it is not just the craters on the moon's south pole, but the regions around it, which are alternately light and dark as the moon rotates on its axis. And so how are you going to feed solar panels with sunlight to do that? And what has happened is an innovative company called Maxar has got a contract with an organization called NASA, who are, of course, sending, they are the agency that is responsible for the Artemis mission. What Maxar has done is proposed something with the innovative name of Lightbender. And Lightbender is actually pretty straightforward in concept. It's a couple of mirrors which will be mounted on a mast about 20 meters high. And remember, no wind on the moon, so you don't have to make this particularly wind-resistant 20-meter high mast. It's 65 feet, thereabouts, in the old measure. And putting large reflectors on this mast, two of them, around about 10 meters across. These are basically 10-meter mirrors, 33 feet in diameter. And then the trick is to use these two mirrors with robotic control so that they will actually point a beam of sunlight where you want it. And it's a diameter beam of sunlight. And where do you want it? Well, you want it on the solar panels, which are on the equipment that you're using, maybe even small solar panels that the astronauts might carry with them to get local power. The real innovative part of it, this is a kind of not new technology. And actually, I think you and I might have talked before about a large mirror which is on top of a mountain in southern Norway.
We did.
Yeah, that bathes a particular village. I can't remember the name of the village, but they get sunlight in their town square in the middle of winter, so that the SADS syndrome, is that what it's called? The seasonal something deficit.
That's right. Winter blues for another term, I think they call it.
That's right. And so that cheers people up, which is a great idea.
Yeah, I love it. And it doesn't hurt anything.
Yes, that's right. This is a development of that, but on the moon. And you need two mirrors because you're looking at a very low elevation, so that even at the top of the tower, the sun is right down on the horizon. So you can have one mirror that picks up the sunlight, sends it to the second one, which does the beaming to the place where you want it under autonomous control.
It sounds very much like the way you see something through a telescope.
Actually, there is a well-known piece of astronomical equipment. It's 19th century equipment, which uses exactly the same principle. It's called a heliostat. And the word tells you what it does. Helio is the sun, stat means stationary. And so it gives you a stationary image of the sun. It's a two-mirror system. And heliostats have been used quite often, for solar observations, obviously. If you're observing the sun, one way of doing it is to have a horizontal telescope, which is fed by this two-mirror system, or you can make it vertical. That's another way of doing it. Put the telescope in a deep hole in the ground. So you've got something that is the telescope itself is stationary, and the image of the sun is fed to it by this two-mirror system. So it's very, very similar to that. And I think the new bit is not so much the mirror layout as the robotic AI that goes into controlling it and sending the beam where you want it rather than where you don't want it.
Yeah. So that would be like a guidance system.
Yeah, that's right. Yeah. So, I mean, with a heliostat, it's basically, it started off in the 19th century just as clockwork motors. You wind it up and away it goes, and it just clicks away. And because, of course, you're only following the motion of the sun across the sky.
Yeah. Well, they can do that with solar arrays on Earth. If you want to spend the extra money, you can set them up so you get maximum exposure through the day, because the panels turn in unison with the sun, or with the movement of the Earth, and you keep a direct connection between the solar panels and the light from the sun, and voila, you get maximum benefit from those solar panels. So this is sort of the same thing, except you're doing it with the light rather than with the solar panels.
I have to say, when I thought about Artemis back in the day, when it was first being proposed, I kind of assumed that they would do that, what you just said, have tracking solar panels, plonk them on top of either a crater rim or a nearby mountain.
Because there's this thing called an extension cord. I mean,
feed an extension cord down to where you want it.
Hang on, no, that's too easy. Let's find a harder way of doing it.
But doing that with the extension cord, you kind of, it's not just like a 10-amp cable that you're using. Would be serious power stuff, and you've basically got to move it around, as you need it. And I guess the great thing about this idea, the Maxar's Lightbender idea, is that you just aim it wherever you want it. The trick is to put your light tower in the right place, but of course, if you're clever, you have it on wheels, and with maybe a lunar rover or something to cart it around to wherever you want it. So the illustration that I've got of this thing, it doesn't have wheels. In fact, the base looks a lot like the base of one of the old Apollo lunar modules, the bases that are still sitting there on the moon. Yeah. Anyway, Maxar are a well-known space company based, I think, pretty sure in the USA, contracted to NASA for the Artemis project to provide beams of sunlight for their solar panels.
Yeah, they've worked with NASA before, haven't they? They've with robotic arms and things like that.
I think that's correct. Yes, indeed. They built the robotic arm, which is currently on Perseverance, the lunar rover sitting on the Martian rover sitting on the surface of Mars, with its little helicopter, which, by the way, fell silent for, I think, 2 months. I don't know whether you saw it.
Oh, no, I didn't.
I think they've re-established contact with it. I haven't followed up on that story.
Yeah. It was a union strike.
The Autonomous Helicopters Union.
Now, with this reflecting the sun onto the panels situation on the moon, are they going to lose much energy in the process?
There's always a loss when you have a reflection. It's if you do things properly, though, it's maybe 1 or 2%, maybe even less. And in fact, that's why with large telescope mirrors, like the one, for example, on the Anglo-Australian telescope, which I was most closely connected with, that mirror it's a large block of, not glass, it's a material called cervit, which is a sort of glass ceramic, which has 0 expansion coefficient, so it doesn't change its shape with temperature. That has a thin layer of aluminium on the front, which is the reflecting surface. If I remember rightly, when it's a freshly deposited layer of aluminium, its reflectivity in the visible wave band is about 95%. But over time, that aluminium degrades, partly because it reacts with oxygen in the Earth's atmosphere to form aluminium oxide, which is not as transparent as you might want it to be, so the reflectivity drops. That won't happen on the moon, so you can probably have 95%, maybe a bit more reflectivity. So there will be a slight loss at the 2 reflecting surfaces, but it won't be.
Yeah, I would imagine that the quality of equipment, particularly the solar panels that they put up there, would be far superior to most of the domestic stuff that we use.
Yeah, it's probably state of the art, which I guess ours are. The one on my roof is probably not state of the art, although it's brand new. But it's a production line thing rather than a research. thing. So yeah, it's doing all right. Well, it's producing power as we speak.
Yes. I'm just wondering, none of us will be around to see it, but I just wonder what it's going to be like 100 years from now on the moon, what the activity will be. And they probably have a big community up there by then.
Yeah, with lots of defunct light benders that don't work.
Maybe. Yeah, maybe. Yeah, it'll be. I suppose we can speculate and probably get a very accurate idea of what it will be like. But yes, it's going to be fascinating. No, it's going to be fascinating, I think, because it is going to be the stepping stone to travelling beyond the moon to other parts of the solar system.
The aim is to have continuous habitation there. I don't think the aim is colonization, at least I hope not, because this is where we belong. But yeah, basically the idea of having a permanent presence on the moon, which is great. It's a bit like, the step that was taken in 2000 to put a permanent presence in space with the International Space Station, which has been extraordinarily successful.
Indeed. All right. Well, as we get closer and closer to sending people back to the moon, there'll be lots more exciting stories to tell. So we'll keep an eye on it for you. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, to a story that has gained a lot of momentum recently, and that is the expansion of the universe. We get a lot of questions about it. We get a lot of people who are confused about certain aspects of it, and rightly so. It's indeed a mystery in many ways. But now there are claims that the expansion of the universe slowed after the Big Bang, which sort of is counter to what we think is happening now, which is the acceleration of the expansion of the universe. So what are we talking about here?
Well, something a little bit different from that, in fact.
Okay.
We're talking about our perception of the ticking of time as we look back. Let me just stop for a minute, though, and say that you're absolutely right. The expansion of the universe did slow down after the Big Bang. Because we had this period that we call inflation, which we think started something like 10 to the minus 33 seconds after the Big Bang occurred. And that period of inflation lasted about the same length of time, a gazillionth of a second. But the universe expanded by a factor of about 10 to the power 50 or something like that in that brief instant. So the expansion period was slow. Sorry, the inflation period was followed by a slowdown. And I think it's fair to say that physicists do try and understand why this all happened, but I think the jury's still out on the reason why we had inflation and why it slowed down afterwards. So you're right that the expansion did slow down dramatically, in fact, and is now accelerating. So we think the reason why the acceleration's only kicked in the last 5 billion years or so is because the gradual expansion earlier separated galaxies, so their gravity wasn't, they weren't feeling the gravitational pull to the same extent as they were, and the dark energy has managed to overcome the gravitational attraction of everything in the universe, if I can put it that way.
Yeah.
So we now have an expansion. But what we're talking about today is something a little bit different, and it is our view from our vantage point 13.8 billion years after the Big Bang, our view backwards through the history of the universe, which of course we can do because of the finite speed of light and radio radiation. And the expectation is, because the universe has expanded, that expands, light waves, we know for a start, which is why we have redshifts. The longer a beam of light will travel through an expanding universe, the more its wavelength is stretched. And so, for example, the flash of the Big Bang, which we can still see, which 30.8 billion years ago was brilliant white light, now microwave radiation because the waves have been stretched. But a consequence of that is that if you look back from our vantage point, not only will you see stretched wavelengths, you'll see stretched time, if I can put it that way. So that if you think of a clock ticking back in the day, maybe 10 billion years ago, when we look back at that, if we could see it ticking, the ticking would be much slower because of the fact that the universe has expanded in the intervening time. So we should be able to look back in time and see time dilation. And that has been done over a number of years by something to do, and this is not quite the story we've got today, which I'll get to in a minute.
Okay.
Be patient, be patient.
Oh, I am.
You are. You're very patient. You'd have to be to talk to me. The most perhaps well-known example of this is what we call supernova light curves. So when a star explodes, and there are different mechanisms for doing this, but let's just talk generically. What you get is the star explodes in a supernova. You get an upturn of the amount of light. You see the light increase in intensity, and then it gradually fades away over time. The light falls off. So that's what we call the supernova light curve. It goes up steeply and falls away slowly. And we know kind of how long that fall off lasts because we can see supernovae in the relatively near universe.
Yeah.
And it turns out that when you look back, say, 5 billion years, that light curve is stretched. So the increase in brightness followed by its slowdown takes longer when you look at things in the distant universe than it does in the nearby universe. And that's because our view of the time is showing it slowed down. You've suddenly got blurry.
I have, haven't I? Because I moved something. I'll see if I can. Oh, there it is. I just had to move my microphone because it was getting in my face.
Because I'm looking back in time, you'd got blurrier than you were. Anyway, the bottom line is that with supernova, you can see this time dilation effect. So scientists know that it happens. It's predicted by relativity and all the rest of it.
Yeah.
But the reason why this story is in the news now is that Geraint Lewis, a colleague and friend from the University of Sydney, and his colleagues have observed a kind of ticking clock in distant quasars. Now, I have looked at I've actually got the abstract for the paper here. Their paper is called The Detection of the Cosmological Time Dilation of High Redshift Quasars. Quasars a long way back in time. But the abstract doesn't give any clues about what the clock tick is that they've used. I think what they've done is probably they've looked in multiple wave bands. So I think they've looked at phenomena that might have delays in their different wave bands. And it's that delay that they've counted as the tick of the quasar clock. What they're seeing, though, is from our vantage point in 2023, looking backwards about 10 billion years. So these quasars are, the universe is only a couple of billion years old, 3 billion years old at that time.
Yeah.
More than that. Anyway, what they see is the ticking of the quasar, if I can put it that way, is 5 times slower than what it would be today. That's bottom line. And so it's this time dilation effect which is observed. It is observed, and they are essentially matching exactly what you would expect at these distances. Let me just read the first sentence of the abstract, which I hope explains it better than I've done. A fundamental prediction of relativistic cosmologies, in other words, histories of the universe, is that owing to the expansion of space, observations of the distant cosmos should be time dilated and appear to run slower than events in the local universe. That's the bottom line. And they found it 5 times slower. It's a fantastic observation. I will read the paper, the article itself. It's published in Nature Astronomy. So I might find out a bit more about what they've done. It's possible I might even run into Geraint in a meeting I'm going to tomorrow, so I can ask him face to face.
Yeah. I recall a question coming in this week that kind of talks about that, and I'm just wondering if I could squeeze it in, because it does talk about the issue of time in relation to a black hole. And I don't know if I can play this because I didn't actually load it properly, but I'll give it a crack. This comes from Carrick, so let's see if we can get it sorted out if the blue ring of death doesn't stop spinning.
Hey there, Space Nuts Podcast. This is Carrick from New Zealand. I had a little bit of a question in relation to a thought that I've been having about the movie Interstellar. Obviously, there's a point in time when they're close to one of the black hole gargantuan, I believe, and whoever's on the planet, their time is moving much slower than their colleague who is up in space, and he ages much quicker. The thing that's been baffling me, however, is the fact that even though time is moving faster for the team that's on the planet, they still stay the same age. However, their colleague up in space obviously gets much older. I know that time is obviously something that not created by people, but we've made it equivalent with numbers to make it comprehensible for us as a human. But I don't understand how the people up in the spacecraft, obviously their bodies would age at the same time, regardless of where they are, or is my thinking completely out of the plot? Thanks very much for that, guys. Hope you have a lovely rest of your day, and thanks for the podcast. I love listening to it on my journeys. Thanks. Bye-bye.
Thank you, Carrick. Have you seen the movie Interstellar, Fred?
Yeah.
Yeah, and so you know the part where they've parked it outside the effect of Gargantua, the black hole, but then the planet that they're going to is within that effect. So for every hour you're on the planet, 7 years passes on the spaceship. Carrick is having trouble absorbing that. He doesn't understand why that would be, and if it's a real potential situation.
So the reality of it is, I think that's fair enough to say that. And this is true of what we've just been talking about as well, the time dilation effect with the expansion. It's a similar phenomenon. To the participants at these two places, one on the planet, one in the spacecraft, their time just passes at the same speed. What's different is your perception from one to the other, that's the difference. Because to each of them they'll age at the same rate, but they're relative one to the other. They age at different times. I don't know whether that explains it.
Yeah. So, and that is because of the gravitational effect of the black hole.
Yeah, that's right. That's
it's warping time, basically.
Yes, that's right. Gravitational time dilation. Exactly that. We know that happens. We know, in fact, you can measure that effect on Earth just with the gravitational potential of the Earth. You can fly very accurate clocks on spacecraft, which are in orbit 400 kilometers away, and they experience time at a different rate from what we do. But to anybody on the spacecraft, the time is ticking at the normal rate.
Exactly. Yeah. It's the same as the speed of light factor. As you get close to the speed of light, is it time dilation there as well? Is that what it is? Yeah. So Carrick, as portrayed in that film, it could happen that way. I think they did a lot of, there was a lot of creativity in that process, but maybe not 7 years per hour, but there would be an effect for sure.
I sort of saw that as a kind of comedy movie.
Did you?
Yeah. Well, all the physics that we know and love is twisted to make a bit of a joke of it, really.
Yeah. Or just, never, as I say, never let the truth get in the way of a good story. My favourite part of that movie? The soundtrack. I love the soundtrack. Is amazing. Yeah. I'd watch it again just to listen to the soundtrack because it fits in so perfectly with what you're watching. And that's the secret of a good soundtrack. Yeah, I've watched it about 4 times. I love it. All right. Thanks, Carrick. And yes, we are perceiving time differently as a consequence of whatever Fred was talking about. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Okay, Fred, while we're talking questions, let's tackle a few. And a regular contributor to our question segment, although we haven't run one of Buddy's questions for a while, And these also relate to what we were just talking about with our perception of time. Buddy's got an interesting one as well.
Hey guys, Buddy in Oregon again. I've been struggling with something. Is there a time shift inside a galaxy as you get away from the center of the galaxy? Is time going to be speeding up? So like if we were further out in the loop of a galaxy, would time actually be moving faster than when if we were on a planet towards the center of the galaxy? And if that was true, when things are rotating away from us, it has a redshift, right? Well, when things are rotating away from us, would there be a time shift also? I hope that makes sense. Thanks, guys. I'm a huge fan. Keep up the good work.
Thank you, Buddy. I suppose Buddy's question is an example of how very confusing this situation is. But okay, where we are compared to, let's say, another civilization on a similar planet closer to the center of our galaxy, is there a time difference or a difference in the perception of time as we've been discussing?
It's exactly this difference in the perception of time. So that there will be, because galaxies are it's got enormous gravity, 400 billion stars. Its gravitational potential is not the same as a single star or a single planet, but it's still there. And so to an observer sitting out in the suburbs like we are, if we could observe things going on in a planet nearer to the galactic center, exactly as you've said, they would appear to be slower because of gravitational time dilation. So once again, it's the relative difference between the two. That's why it's called relativity. It's all about you're looking from one place to another and seeing the relative motion of one or the relative time ticking. So Buddy's right. It would be, but it doesn't. But to the person on the planet near the center of the galaxy, time will be just ticking away at the same rate as it is to us. They might look out and see all these people on planet Earth moving around frantically because they see, their time their perception of our time is speeded up.
It would be like looking at an ant nest after you've walked across it and they're all freaking out.
Yeah, they would. That's right. Especially those bull ants that you've got.
Oh, yes. We've got some nasties out here, haven't we? Yeah, I remember them. Yeah. Reminds me of when I was a kid and I was at a scout camp, and on the Sunday, the family was allowed to visit. And my sister and mum and dad came along, and I don't know if you've ever heard of those big jumping ants that we have in the bush. They're about, 1.5 inches long. They're big buggers. Well, she stood on one of their nests and they swarmed her like she was screaming in terror and pain because they bit her. But that was horrific. But, we got some nasty snakes, nasty spiders. We've got nasty ants here as well. But back to Buddy's question, the observation of time would be the same to us as individuals in our presence, but looking at, and if we had a Looney Tunes telescope and were able to look at another planet and watch the people, if they were closer in our galaxy, closer to the center, we'd be seeing them in slower motion. But looking out, they would see us sped up like a silly old black and white film,
or an ant's nest.
Or an ant's nest. It's a weird concept, Fred. It just freaks me out.
Very odd. Yeah, and I'm not surprised it freaks out Buddy as well, because it freaks me out. What keeps me sane in this is the equations, which when you look at them, they tell you, this is what happened.
Back to good old mathematics. It always has the answer. It's rock solid. Thank you, Buddy. Now, not dissimilar to that, but a more basic question from Colin.
Hello, Andrew and Fred. This is Colin from Adelaide, South Australia. I've always wondered how you can tell the difference between, say, something 1 million light years away and something 5 billion light years away. In last week's episode, Professor Fred mentioned this is done by measuring redshift. Can you please explain what redshift is to me, please? Enjoy the show. Keep up the good work.
Thank you, Colin. Pretty simple question. You did actually explain a bit about redshift earlier in the show, but maybe we can sort of broaden that a bit.
Yeah, I think it's something worth talking about a little bit because it kind of gets confused with something called the Doppler effect, which I guess we're all familiar with because we hear it in sound all the time. The fact that, something making a noise coming towards you, and it's usually a siren or something like that, sounds higher pitched when it's coming towards you than it does when it's leaving you.
Yes.
And the same thing happens with light. So that's how we measure the velocities of stars in particular, and planets. Anything that's giving out light, you can see how its light has, its wavelength of its light has moved relative to our movement. And so, in fact, I spent a large part of my career doing this for stars, something called RAVE, the radial velocity experiment, where we measured 500,000 stars and their velocities by this Doppler effect. As stars move towards you or away from you, their light is shifted slightly to the red or blue end of the spectrum. Redshift is a little bit different because it's technically not the Doppler effect. The redshift is caused, as I mentioned last week, by the fact that as radiation travels through the universe, if you're traveling for a long time through an expanding universe, then the radiation waves themselves expand. And so you get this shift from whatever color light it was when it was emitted, whether it's infrared light, radio waves, or optical visible light, then it's the longer it moves through an expanding universe, the more its wavelength is increased. And it's by precisely measuring that increase that we can actually determine how far away something is, because what you're saying is, in fact, it's more of a look back time rather than how far away it is. You're saying that when the light left this object, its frequency was something we know, but now its frequency has dropped or its wavelength has increased, the two are equivalent. And by measuring that, that tells you how long that light's been traveling. That's the bottom line. It's an exact measure of how long the light has been traveling. And that's the effect of the redshift. So that's how we can, something 1 million light years away would certainly feel the effect of the expansion of the universe. You'd see a redshift because of that. Something a few billion light years away is a much bigger redshift, and once again, you can measure it precisely so you can get the difference between the two.
How, though, do you know what the frequency was at the time that the light was released from the object?
Because of our understanding of the way atoms work. So
Mathematics.
Well, yes, it is really. We know that, for example, if you excite a hydrogen atom, it will emit light of a particular color. In fact, several colors, but the most common one is a light which gives you a particular red color, which we call hydrogen alpha, and that you know the mechanism of the behavior of the atom to emit that light. The atom always behaves in the same way and emits light of a certain frequency or wavelength. And it doesn't matter when in the universe it does that. It always emits light of that frequency.
Okay.
So, even something back in the first stars, when they started emitting light, the hydrogen light that they emitted would have the same frequency as an atom of hydrogen doing the same thing now. That's your standard. That's the frequency standard.
Okay. Very good. All right. There you go, Colin. Easily explained.
I hope so.
Nice to hear from you too. One more thing before we wrap it up, Fred, and this is not a question. This is something that's close to your heart. You like to play the guitar and write songs and sing, don't you? Yeah. So does Martin. Are you ready for this?
Oh, let's go.
Oh, boy. Here we go.
Hello, Space Nuts. Martin Berman-Gorvine here, writer extraordinaire in many genres, wanting to know what you think of this song about the search for alien life. Hit it. You thought that you'd never know back when I was UFO, that Drake equation so slow, and how it's UAPs. You trade your soul for a wow. If I would tell you just how to reach FTL right now, if only I just sneeze. At that water hole, you thought you'd reach your goal. To hear me, you'd sell your soul. Why don't you listen, baby? Hey, you just got back, and this is crazy, but here's my redshift. I'm out here maybe. It's hard to find me, so many stars, but here's my redshift. I'm out here maybe. Hey, carbon's common. This is so crazy, but here's my redshift. I'm out here maybe. And all the SETIs, they try to chase me, but here's my redshift. I'm out here maybe. Eat my dust, Enrico Fermi.
Oh, dear. Oh, my. That was so clever.
When he said writer extraordinaire in many genres, you didn't expect that.
No, I didn't expect it. When I was going through the questions for this week, I just, I generally just click play to listen to them so that I know what's going on. And I just sort of sat back and went, wow, we've got to play it.
Yeah, we've got to play it. I love the sentiment, Martin. I'm out here maybe. Because that's bottom line, really.
Yes, indeed.
Maybe not, but maybe, yeah. Fantastic.
Yeah, terrific.
Right,
yes.
Everything's in that. It's great.
Not the first one to send a song in, and it's, Paul is way overdue to write us another one. Way overdue. Thank you, Martin. That was wonderful. Don't give up your day job. Fred, that brings us to...
I think people tell us that as well.
They do. I know. Oh, dear. That's the end of the show. Fred, thank you so much.
It's a pleasure. Always good to participate in Space Nuts while the going's good.
Yes, indeed. And thanks to everyone who's contributed. We've still got a bunch of questions to get through, but please keep sending them in to us because we love to hear from you. And if you've got something that's gnawing at your brain, I'm sure Fred can figure it out. Whatever it is that's gnawing at you, that is not the answer. But send us the questions anyway via our website, spacenutspodcast.com. Spacenuts.io is the other URL, and you can click on the AMA tab up the top where you can send us text or audio questions, or on the right-hand side of the homepage, send us your voice message. And tell us who you are and where you're from and ask your question, and we'll chuck it into the mix, unless it's already been answered. Sometimes we get the same questions many, many times, but yes, we'll do our best for you. And while you're on the website, have a look around, see about becoming a patron. And thanks to our patrons. I haven't said thank you to you for a while, but we appreciate your support. Don't forget to visit the Space Nuts shop while you're on our website. Fred, thanks again. We'll talk to you again real soon.
It sounds good, and I'll look forward to it, as always.
Thanks, Fred. Professor Fred Watson, astronomer at large. Thanks to Hugh in the studio for being Hugh in the studio. And from me, Andrew Dunkley, it is goodbye. We'll catch you on the very next episode of Space Nuts. See ya.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.